This video looks at how you can create an unbiased performance index. We have established in the previous few videos that a performance index comprising quadratic terms is likely to lead to easier optimizations and smoother outcomes. However, we've also shown that a naive use of quadratic terms does not lead to a sensible outcome. So this video introduces the concept of an unbiased performance index, which is what we need to ensure the optimizations are well posed and give us sensible answers. Now, we've shown that the performance index should logically penalize tracking errors and input activity, because what you want is for the tracking errors to go to 0 and the input activity to be small. But a simplistic realization of this does not work. So if you just use a J, which is a sum of tracking errors and input activity, as we've shown there, and you note that in the steady state you have a constraint, something like this: y steady state is the steady state gain g times u steady state. If you plug in the steady state values to this performance index, you end up demonstrating an inconsistency. That is, it's not possible for the steady state output to match the steady state target. It doesn't coincide with the minimum of this performance index. So you can't converge to the correct target. And why is that? Because you can't drive the error and the input to 0 simultaneously. So I've repeated that here. It's not possible in general to drive both the error and the input to 0 simultaneously. That's probably fairly obvious to you. If you want the tracking error to be 0, then the input's going to be non-zero. Whatever input you need to get the output to the required value, that input is not 0. And similarly, if the input is 0, clearly you'll have a large tracking error unless your target was 0 itself. So what do we need to do? We need to think of a different way of approaching this. What we want the performance index to deliver is something like this. We want it to be optimized when the steady state value of the output, YSS, equals the target, when clearly the steady state value of the output is given by the steady state gain G times the steady value of the input, so that's G USS. So we want the performance index to drive you to this operating point. And so a simple idea that's fairly common in the literature is to penalize the deviations, that's the key word, the deviations from the desired steady state. As by definition, if we drive those deviations to 0, then we have to be driving y to r and u to the relevant steady state value. And unsurprisingly, you'll think, well, we've looked at deviations in the previous few videos, so we can define a deviation in the output as y minus r, or perhaps I'll be better writing it as r minus y, but it doesn't matter, it's makes no difference. The deviation in u as u minus uss. And therefore, if we construct a J which is comprised of the sum of deviations squared in the output, deviations squared in the input, then clearly that J is going to be unbiased. Now, in an earlier video, we looked at unbiased predictions, and we proposed the following for state space models. We said, first, estimate the steady state values of the disturbance states and inputs to ensure consistency between the model and the process, and thus define deviation variables. So what we said is, if you can estimate XSS and USS and YSS to be mutually consistent with each other, then you can get unbiased predictions. And from that, we define deviation variables x hat for the state, u hat for the input, y hat for the output. And what you'll notice is these deviation variables which we've used in our prediction model are exactly the same deviation variables we want for our performance index. And we showed that you could get a prediction for the output in terms of deviation variables as a function of deviation variables in the state and deviation variables in the input. So what's our summary? If we use unbiased predictions in combination, so unbiased prediction in combination with an unbiased performance index based on quadratic terms, so you'll see there's 3 concepts in there, then you will expect to get a sensible outcome. And specifically, this is the key point, if you do a steady state analysis, you can show that if, that's a big if by the way, I'll circle that several times as a big if because we haven't guaranteed it yet. The closed loop system converges. It must converge to the correct steady state. And so what we have is a performance index based on deviation variables, and we have predictions based on deviation variables. And so we have a consistency which says that if you are at the correct steady state and you don't change the input, then you're going to have u future hat equals 0 implies y future hat equals 0. So that's what we got from our unbiased predictions. So we said if you're already in the correct steady state and you propose that you don't change the input, then your prediction should give you the output does not change. So that's what I've put in this red circle. And clearly, if you minimize this performance index over here, the smallest you can get is 0 because you've got sums of squares terms, and you can see that if you put u future equals 0 and y future equals 0, you do indeed get 0. So these are consistent, which is where you get the statement here, if the system converges, it must converge to the correct steady state. Now, a bit of a warning here, which we've just put down in this box. Whether you converge or not, and tuning, etc., are topics for later videos. What about alternative performance indices? Well, the key attribute we wanted for the performance index is that it's unbiased, and we can actually think of other unbiased performance indices which don't affect the steady state. So in simple terms, something's unbiased if, when you're at the correct steady state, minimizing the performance index tells you that the input should not be changed. So in other words, you stay at the correct steady state. Now the most obvious terms are those which themselves are 0 at the correct steady state. And some common components, and hence a generic choice of J, that satisfy this requirement can be listed here. Clearly, you have the tracking error itself. If you're at the correct steady state, the tracking error is 0. You have the deviation in the input, so how far are you from the correct steady state value of the input, but you also have this extra term down here, which is the rate of change of the input. So you see delta U is defined as UK minus 1, and clearly, if you're at steady state, you're not expecting the input to change, you would expect this term also to be 0. Now, you could think of other terms which would be 0 at the steady state, but these are the three most common. And we're assuming, and I've put that over here just to emphasize because this is common in predictive control, people tend to assume that the target is constant when they do this form of analysis. If you have a time varying target, then things would be a little bit more tricky. So, alternative performance indices. Now that we know the sorts of terms we can put into J, then we can give a more generic choice for J. And here it is. We can have a sum of target error squared. We can have the deviation variables. You notice this is essentially U hat. And we can have the delta U terms. And you'll see if you're at the correct steady state, this J can still be equal to 0. And again, we've emphasized we're assuming a constant target here for convenience. Now, it's more typical in the literature to see the following two alternatives. You very rarely see people use all three terms when you read papers. What people will tend to do is either use this one here, which you can see basically penalizes the distance of the input from the steady state. We have the deviation in the input here, U hat. So that's quite common with state space model formulations. If you look at transfer function formulations, people are more inclined to use this form here, where they penalize the rate in the input, so they penalize delta U squared. And you could say, well, that has some sense in it because delta U has a closer link to fatigue, and the actual value of the input is sometimes less important. Now, so far in these videos, we've given the performance index in a very simplified form. We've used the same horizons for the inputs and the outputs, and we've used scalar weights. If you want to be a bit more generic, you can come up with something like this. And what do you notice? You'll see we've got matrix weights on each term. So if you assume that E in U are vectors, then you might want to put different weights on different tracking errors and different weights on different deviations in the input and different weights on the rates of change of the inputs. You'll also notice we have different horizons. We might have one horizon on the output and we might have a different horizon on the input. Now, there is a lot of discussion in the community about the role of these horizons, so we're not going to talk about them in detail in this video, just to point out that there is the possibility of choosing NY and NU to be different, and it may make good sense to choose them to be different. So in summary, the use of quadratic performance index is the most common choice within the literature and tends to result in smooth and robust control designs. However, you cannot naively choose some function of the square of tracking errors alone, as this will not result in good control in general. And what we've done here is we've summarized a typical performance index which ensures the system will converge to the correct steady state, and you'll see the assumption there, assuming it converges at all, which we haven't proved yet. Discussion of the choices within this performance index, such as the weights and horizons, will be covered in later videos. Now, a bit of an addendum. Some in the community feel the use of a performance index is rather artificial, and you remember we did say 1 or 2 videos ago that in fact this performance index is to some extent arbitrary, and therefore you might feel that people in the community who say this have a good point. And what they propose is encouraging, in some sense, the system predictions to follow a given dynamic path, such as a first order response with a given desired time constant. And you'll find this sort of approach can be relatively straightforward and intuitive for simple CISO systems. However, you could also show that this latter approach is equally arbitrary, because you have to come up with the desired time constant, and while that might make sense for simple first order systems with straightforward dynamics, it's not going to make sense if the dynamics are a bit more complex, or if you have lots of interaction and a multivariable process. And so this latter approach does not lend itself, and that's the key thing, to convenient analysis, guarantees of good behavior, constraint handling, or MIMO processes. So what we've got is the intuitive argument is useful for simple CISO systems, but doesn't necessarily extend easily to more complicated systems, and that's why the community at large tends to have stayed with the use of performance indices.